So I'm going to talk about spatio-temporal modeling of landslides. I'll give a bit of introduction on what is the landslides and what are the current problem on modeling the landslides using graph and recurrent neural networks.
Also, so, you're coming in really quiet. I don't know if that's just my end.
Can you hear me now?
Yeah, you're really quiet. Maybe it's just me. Is anyone else hearing it quiet?
I can hear it okay.
Okay. Sorry then, go ahead.
Okay, so
question sorry to interrupt, team. Did you say you were going to record? Is it recording already?
Yeah, I'm recording on my desktop right now.
Cool.
Not through Google Meets.
Okay.
Yeah, so if you can hear me, then I'll continue. So the team that we are working on is me. I'm a PhD student with 4 professors here, Luigi Lombardo, Hakan, Case, Mark, and these are all, everyone is from the ITC in the University of Twente. And we have 2 other collaborators, Professor Rafael Husser and Martin Mai from King Abdullah University of Science and Technology in Saudi Arabia. And they are mostly working on the statistics and geophysics rather than machine learning, but everyone here is more on risk and natural hazards, like modeling how to quantify the environmental problems. And the topics that I'm going to cover today is mostly I'll talk about the definition, like what are the standard terms that I will use throughout the presentation, which data that I used, problem that we are facing in the machine learning part, and what are the methods that I'm using, results and future directions. So with the definition, I think everyone here knows what landslides are. If you don't know, it's just land that slides. So we have pretty much stable land everywhere in the mountains. And when there is a triggering event, let's say a rainfall or an earthquake, the slope fails and then it causes a landslide, killing many people and destroying homes. So to quantify the landslide hazard, it's usually the term that they use is landslide hazard, which is hazard is a phenomenon which has potential to cause a damage, and landslide hazard is quantified as a susceptibility, which is probability of landslide occurring, intensity, which can be quantified as any value, and the frequency, how frequent does it occur. And so in our case, whenever I say intensity, it's area density, which is the total area of landslide divided by mapping unit multiplied by 100. Susceptibility is probability in statistical term, but in deep learning term, it's pseudo probability output of the sigmoid function. And frequency in this case is count, but it can also be temporal frequency. So the data that we are using for this is we have 30 years of landslides mapped through 1989 till 2018. So this is 30 years of temporal data set for landslides. This is how the heat map looks like. And these are all done manually from the university in UK, Durham, I think. And they mapped it using Landsat 5 till Landsat 8. They have not used the Sentinel satellite yet, but this is how the distribution of the landslide looks like over 30 years of time period. And let me wait for the animation to finish. So yeah, and these are mostly linked with these events are mostly linked with the heavy rainfall or the extreme events that causes those landslides, and mostly it's on the mountainous region here and in this region and this region. So how does it look like? It's all of them are polygons. So they map the polygons manually, and it is separated as source where the landslide initiated and deposition where the landslide deposited. But we only look at the source because the deposition is a byproduct, but it's not the actual land that is failed. And so for the covariates or the predictor variables that we used, clay content, organic content, mean of the horizontal curvature standard deviation. This mean and standard deviation, it will be explained in the next slide, because if you just look at the pixel level or the image data, you cannot really quantify mean and standard deviation. But I'll explain why I have to use mean and standard deviation in the next slide. And eastness, northness, elevation, slope, and precipitation and DVI for the entire year. So all the landslides are mapped in in a yearly basis. So also the NDVI mean this is the temporal mean, and the precipitation mean and standard deviation is also for the yearly data set. And so mapping unit, as I said before, usually in all of the deep learning, if you use the convolutional neural networks, we use pixel-based patching. So we use usually all the data is in the pixel. So if we patch in 30 by 30 pixels or even more, like it will look something like in the figure in the left, like in a grid. But for this, for landslides specifically, it didn't really make sense, because if we use the grid, then sometimes the half of the landslide is in one patch and half of the landslide goes to other patch, because we cannot really use entire study area as one image in the convolutional neural network. So, and also usually the landslides, they are physical processes. So they follow physical terrain or geomorphology. So it initiates around top of the mountain and then it follows, it goes towards the downside. So instead of using these pixels, we use these units called a slope unit, which is derived using the watershed. So we have a big watershed and then we constantly divide it to smaller slopes until we can really identify one slope unit or one slope or one mountain face. So it looks something like this in 3D. The red lines are the slope units. So we aggregate all of our data in these slope units and do the modeling using graphs. I'll explain later on how do they work. So for this, we calculate area density, total area of landslides within these slope units multiplied by the total area of slope units, number of landslides, how many they occurred, and whether there was a landslide or not. So it's 0 and 1. So we aggregate all the data into slope units instead of just looking at the grids. And with that, we come to the problems. So I'll not explain about the societal problems or environmental problems. Those are pretty much established. I'm going to talk about more of the problems on modeling. So the first one, as I already mentioned, mostly all the existing work, they use convolutional neural network, and then it's all in image size, but landslides usually tend to follow pixels. And also when we do the risk reduction, like when we want to make a wall to prevent the landslides, it's usually done in the mountain face, not exactly in the pixel. So identifying which pixel might fail and going to the field is more difficult, I guess. And also spatial dependence. So dependence between the mountains is or the slopes is usually occur in the slope units. In the pixels, it's kind of homogeneous. So the basic consideration of the slope unit is they are a homogeneous unit with similar slope, similar precipitation, and other factors as well. So challenge with first challenge in predicting where does the landslide occurs, because we need three components: where, how big, and how frequent. So for the component where, we have one big problem is the data is extremely unbalanced. So when we had 290K landslide absences in the slope units, we have just 12K presence of the landslides in the entire 30-year data. So we have 12,000 landslides, slope units that have the landslides, and 290,000 slope units that didn't have the landslides. So the ratio is very big. So modeling this extremely imbalanced data is a challenge. And the second problem is predicting how many it's a bit more easier than predicting how large they will be. So it follows a Poisson distribution. So there are a lot with a 0, and then it increases like it decreases with an increasing number. So it's like a Poisson distribution in log scale. But it has a bit more less impact on risk reduction, because once we know which slope units are failing, we might need to also do the physics-based simulations to understand how the landslide actually occurs. And the major problem, and I think the most challenging task, is to predicting how big. So if you look at the distribution of the area density of landslide, it's actually everything is 0, and then you cannot really see remaining. So if we remove just the 0 ones and look at the distribution, it follows something called extreme value distribution. So there is a statistic branch in statistics called extreme value theory and extreme value distribution, where they use this to model extreme values. And usually in landslide science, though, they just transform it using log and then use Gaussian distribution to model. But the problem with that is Gaussian distribution, if we consider anything Gaussian, modeling it on mean is very good, and then plus minus 2 standard deviation is good. But after that, in the extreme tails or the heavy tails, it's very difficult to get the accurate values or good prediction. And that is a problem for us, because if we model all the landslide with average size, let's say the medium sized landslides, but we fail to predict the biggest one or the very largest ones, then actually it's a big problem. Because if we underestimate the landslide size, it might have a big impact on the human life or infrastructure later. Because if we say the landslide is going to be of average size, but if it is an extreme one, then it's a problem. So it shows like up to 65% of the slope unit was failed. So if you think in a real world problem, if 65% of the mountain face, one side of the mountain is failing, that's quite a lot. And if we do not predict them well, these landslides are the most devastating ones. So this was the major challenge for us to model. And to model all of this, we created one sequence of the different type of layers. The first one, because we have the data in space and time, so we have 30 years of temporal data, and we have a spatial component for every year. So first we look at the space, we model the space, and then we model the time, and then we create, from that we branch out 3 different outputs. So estimating where, how many, and how big. So for space, we use graph neural network, and for time, we use GRU, or gated recurrent unit. We follow space by time because mostly because it's a rainfall-induced landslide. So if there is a landslide in this year, the dependency between variable will be most likely to occur in the same year, and then the influence of the landslide, influence of the rainfall that happened previous year will be only most likely to be only in the same slope unit, and the assumption here is it doesn't really affect the neighboring slope units. So first we model the space and then time and then multiple outputs. So the spatial dependency, or let me put it in this way. So in an ideal scenario, if we could have all the data set that we need, we do not actually need to model the spatial dependence, because one slope unit is considered as a homogeneous unit, so it should be able to provide all the predictors to predict the landslides. But the problem here is we don't know all the predictors. We don't know the geotechnical parameters. We don't know how deep is the soil. We don't know a lot of things. So we are just using proxies, and with the law of geography that all nearby things are correlated. So we try to gather those information by looking at the nearby slope units or nearby mountains. And this helps to get a better prediction. And to do that, we convert our slope units using to a neighborhood matrix, to a graph. So this is how the graph looks like in bigger. But if we zoom in, for each slope units, it will find all the neighboring slope units and define these adjacency metrics, or the adjacency where this length is, so the weights, we have to assign the weights. So the weights are inverse of the distance, and all the centroid of the slope units are connected through graphs. That's how we know like which slope unit is the neighbor of which other slope units. And to model the space, the model is a bit more complex, but I'll just put it in a simple way. How does it work? Is it looks at each slope unit. Let's say I already defined a graph here. So for one slope unit that is in red, it looks at the neighbors, like all 3 neighbors, and it uses some sort of function, which is the neural network itself, and multiplies by some weight. And this component, which is the neighborhood influence, is, let's say, Zij for all of the neighbors. So it sums up all of the neighbors and their weight. So the weight is inverse of the distance, and the function is the neural network, which is weights plus biases, weights multiplied by x plus biases for all the features that we give, all the input predictors that we give. So this neighborhood influence is added to the actual data where we have function multiplied by all the properties in the node plus which is alpha, which is a regularization parameter, plus this neighborhood influence. Basically, it looks like this, but all of these parameters, the alpha and the function itself, is learned through training, and it can be tweaked to make it a bit more complex. And how does it work is we give the graph, and it goes through all of the nodes, then uses a ReLU, and then goes to next nodes, and then uses a ReLU up to the last point where we go to the temporal component. And for the temporal part, we need to also model the temporal part because there is something called legacy effect. So if we had very heavy rainfall this year, and there was no landslide, then maybe next year the water table is maybe high, the groundwater table is high, and when the next year another rainfall occurs, it might cause a landslide. But this effect is like it's slowly exponentially degrading. So this the first year is the Q1, and then when you go to second year, the effect of the first one is almost half, very less, and when you go to third one, the effective first one is less, and then additive effect. So it's just the additive effect that is more using GRU, gated recurrent unit. So then now we have all the special dependency for each year on the graph. So now we process, now we pass the entire graph to a gated recurrent unit to understand how it affects in the temporal part. And after we have this part, then we need to get three things. So we just add, like we just branch out three different densely connected networks, densely connected layers to calculate where the landslide will occur. And based on where, then it calculates how many and how big. So if the source probability is greater than 0.5, it will be calculated, otherwise it just sets to 0. But actually in the code, it calculates for everything, but if it is less than 0.5, then it just multiplies by 0. And so for the part where, or for the susceptibility part, we have 12 blocks of this dense network, class normalization, leaky ReLU, and dropout. Dropout is for preventing model from overfitting. And the last layer of the model is sigmoid. So it gives probability, like pseudo probability, not exactly probability. In statistical term, it would be probability, but here we call it pseudo probability from 0 to 1. And this we treat it as a susceptibility. And instead of, because the data is extremely imbalanced, instead of using binary cross entropy, we use focal Tversky loss. So it is calculated using, we have Tversky index. It's very similar to dice loss though. So we have Tversky index, we have two regularization parameter, alpha and beta, which can regularize how many false negative or false positive we can have. And then it's then taken as 1 by gamma, which is another regularization parameter. So we use focal Tversky loss for this. Then for predicting how many, we have 32 blocks of dense network, the same block as before. And at the last layer, we have exponential layer. So we convert all the data from ReLU to count, and then we convert it into integer and use Gaussian loss. So we have predicted y minus yi log y predicted I. For the entire batch, the n is the batch size. So for entire batch, we calculate the Gaussian loss and optimize. So all the optimizers are Adam. So for everything, we use Adam. And then another problem comes. The most complex one is how big, where the extreme value theory comes in. So generalized Bayes distribution is a extreme value distribution. I'm not going on detail about it, but it's very similar to let's say normal distribution, but it has three parameters. Normal distribution has mean and standard deviation, but it is a bit more complex. But we change this. We use this as a final layer of the model, and we produce the log likelihood. So if you normally look at the deep learning, we use, for the regression problem, we use maybe mean square error or mean absolute error as a loss function, which are obviously the negative log likelihood of the normal distribution. So here we use generalized Pareto distribution as the final layer and minimize its negative log likelihood or maximize its log likelihood to get proper outputs and to produce the actual area density, because we need to understand the hazard, we cannot just say use the probability values. So we need to get the actual area density, and one of the property of this kind of distribution is you need to have a exceedance probability. You can say, okay, so what is the probability of exceedance for 10% or 20%, and then only we can get the actual area density. So it usually depends on the requirement of the government, but we can we tried with 50%, but it can be any values. So in this case, so what we did was we fitted this model. And before that, we used the railway activation to get the proper value of the model. So how does it work is during the training process, we have ReLU before here because all the shape and scale parameters should be positive and the concentration parameter is fixed. So we already know what it should look like. So we fix that other parameter and then we optimize the model for shape and scale parameter, and we calculate the log likelihood of the generalized Pareto distribution and minimize the negative log likelihood of that. And during the inference, or when we have to actually predict it, we say we put a exceeding probability threshold for 50%, 0.5, and then we say if it has the probability of exceedance 50, which is also similar to susceptibility, this will be the actual landslide, actual area density of the landslide. So positive part of this is so it's a more explainable result. We can have multiple values based on the different threshold that we can use. I mistakenly put minus instead of plus and plus instead of minus, but anyway, it's more realistic for risk reduction. It's more useful, but it's very difficult to train because this distribution itself is very complex and it has a very different shape. So training this was very difficult, but we managed to get some results out. So looking at the results, I don't have the maps yet. I just have the F1 score and values. Maps I'm still making. And also I have to get the rainfall scenarios for future to make the proper maps because it's the past data I all used for training and validation. And in the validation, we could get, for predicting where, this is the binary classification problem, we get 93.24 F1 score. For predicting how many, we calculate, we use this multi-class, how to say it, confusion matrix, and say, let's say 0, 1, 2, 3, 4, 5, up to 10, and then we calculated the overall accuracy, which is 82.5%. And for predicting how large, we have root mean square error 0.13, but this does not mean anything if you don't really, in accuracy, it's easy to say what it is, but just looking at the root mean square error, it's not very clear. But I can show it as how good we did as a observed versus predicted area density on a scatter plot, where this is our observed values, predicted values on a validation data. So we don't have up to 60, so it has around 35, but we can see it has predicted very well with the R-square value of 0.98. So if you look at it as an accuracy score, it can be similar to 98%, but it's not an accuracy score. But we can see all the extreme values, also the bigger values, are also predicted quite well. A bit more, how to say it, not overfit, but there are few outliers. They are over predicted, but still that's fine because if we are going to reduce the risk, a bit more over prediction is still okay than doing the under prediction and building a less capable infrastructure and then having everything collapse later on. So and there are few values they are not predicted very well. That's I guess maybe because of the rainfall data that we didn't have properly, or the data set that we used, the predictors were not properly managed. But obviously we'll always have some errors. And future direction is first, we would also like to know what is the uncertainty. So I'm working towards uncertainty quantification and also domain adaptation, because the major problem with the first one is the aleatory and epistemic uncertainty that we want to understand how it is. And also one major problem with the deep learning, or in general in machine learning and deep learning, is if we train our data in one domain, let's say in Nepal, for let's say 30 years of data, 30 years of observations, it will perform very good within those range, like there's those range of rainfall or that domain. But if we, let's say, move it to a bit west to India, or let's say because of the climate change, if the rainfall increases in the next few years, the model will likely to perform a bit bad. Like it will not be really good at predicting the outside of the domain that it was trained on. So we are working on domain adaptation problem, where we could actually train the model. So we have already trained the model in a supervised manner. So now we add unsupervised component to, let's say, adapt the model for newer scenarios or newer domain of the data. So that could be a way, because this is one example I like a lot from domain adaptation problem. Is if the model was trained to fit up to here in this region, it will perform very good here. But if you go outside of the domain, in the higher end or the lower end, then it does not really predict very good. Like here it went straightly down, and here it went kind of very bad. So this problem still needs to be addressed if we want to really use the model to solve for the future problems, or to use it to reduce the risk in the future. Because if we are building infrastructure to reduce the risk in future, we need to also consider the climate change and other factors too. So also other future direction may be explanation of the outcomes, like why we get this outcome using explainable AI, and causation, or like all the problems that we see now is more of a correlation problems, because we see the correlation and we use it to predict. But we could also use causal inference or causal statistics to make it a bit better tool, and usability of the model, like how we can use it at multiple locations. Because in Nepal, it's a special case that we had 30 years of data, but in other countries, if we want to use it, it might be a problem. And I forgot to mention it before, for the temporal dimension, we used 5 years of interval. So we used for every 5 years. So the model can still work for 5 years time period. And I think that's all. The course is not published yet. I'm still trying to improve it. And once we submit the preprint, I'll put the code in GitHub. All the modeling was done in the geospatial computing platform at Saudi Arabia. They have a very huge computing infrastructure there. So I use their computer platform, and all the data preparation was done in Google Earth Engine. Thank you. If you have any questions, please let me know.
Wow, that was fantastic. Thanks so much. I'm going to just pause here if there's anyone else who has any questions on the line. Go ahead, Biplav.
Thanks, also great presentation. And it's also very good to see that using some of the explainable AI, and not just using some sort of black box, which machine learning has been accused of sometimes.
Yeah.
So I was wondering, I know you're still to do validation work for Nepal, but I was wondering if you could also use some of the hydrometeorological parameters to also maybe look in the forecast sort of direction for landslides. I don't know if you have thought about it, or
yes. So what we are doing is the model is ready now. I'm still working on the domain adaptation problem so that it can be used for predicting the future events. And we were planning to use the climate change scenarios of rainfall for next, let's say, 50 years, and use the same model, but also with the domain adaptation problem solved to predict what will be the landslide scenarios in next 20 years or next 50 years on a 5-yearly basis, because the temporal component only works for 5 years. So in every 5 year, how does it work? But we can also actually shift the time and say every year, but 5 years sounds a bit more better. So we were also in Nepal. Usually, it's the plan was before they used to do it for 5-year plan. I think they learned it from Russia or something. But yeah, so yeah, we are actually looking onto it for the future scenarios.
Okay, thank you. And I have one more question. So is there a
Yeah.
partner you're working with in Nepal? Because with Surveyor also we have a couple of landslide projects that probably team can update on. So yeah.
No, actually, in Nepal, we only know few people that they are working on, like in TU geology group, but not really. We are working mostly from the data that is already available online. So if we could get like better rainfall scenarios or the station data and downscale the rainfall, it could be a bit way more better, because now we are using the CRIPS data from, I think, UMD, like University of Maryland, I guess. I just know the UMD, but I don't know the full form. So it's 5 kilometers data. So if we could have, let's say, a better resolution of rainfall from Nepal, that could be a very good solution.
Awesome. Thank you.
Thank you.
Yeah, any other questions online? Well, I'll hop in and say, first off, I think your slide aesthetics are fantastic.
Thank you.
They look great. I mean, these are fantastic. So I'll be showing these as an example to some of the students I work with of how to condense a really great complex topic into something very consumable and understandable. It's really great. So yeah, Biplav, I'm glad you brought up the point of some of the ongoing severe work. Right now, I know that there's ongoing work on landslides in the Mekong region, and there's also landslide work happening in the HKH region through one of our grad students here, but also through the same principal investigator that's working in the Mekong, Dahlia Kirschbaum and her team. They're working through the HIMET group, which is also funded through NASA. And they're primarily using the Lhasa model and SALAD to do automated detection of individual landslides. And that's one of the questions I had there, was associated with one of your first slides of how you're delineating each of the polygons for what is your landslide, or if those are just coming from the National Disaster Response Group in Nepal.
Actually, it's mapped by Durham University in the UK.
Okay.
They did it manually for 30 years. So that's, I think, a lot of energy and time they invested on. And one of my colleague here, one of my professor here actually worked with Dahlia Kirschbaum, and I know about her work and the Lhasa model. And they mostly work on the rainfall thresholding. So if the threshold exceeds, then there will be a landslide. But I think if we could build based on the past inventory using deep learning model, we could actually get better results. And also, if we, let's say, integrate WRF model or any near real-time rainfall forecast model and feed that continuously and change how, look at it on a daily basis or for a few days how the hazard will change. That could also be a tool for early warning and that kind of stuff. But for that, we still need to work on those things. And for modeling, for mapping, one of other colleague on a different project here is working on building landslide mapping tools using AI on a global scale. But the problem still is it's very difficult to generalize model to work at every location, and we are not entirely sure if the landslide will occur at the same location every year. And also because of the environmental conditions and everything, the problem is not building a good classifier, not building a good model that can actually map the landslide, but to make a generalized model using deep learning that can work everywhere. That's, I think, a big big issue they're tackling on.
Yeah, that's so fantastic. So I'm glad to hear that you're already sort of connected to Dahlia, because she had mentioned that Durham data was coming out, it's about to be released, and I was going to direct it to my grad student to start looking at. So that's really exciting. One thing I'll direct you to as well is through ECMOD, through the Severe GCMOD project, there is the high impact weather assessment toolkit, which is an ongoing weather forecasting system that uses a unified modeling approach. So it has ensembles for lightning prediction and hail prediction and accumulated precip, and that's been running since 2018. And that archive is going to be released through the Global Hydrology DAC here in Huntsville. So we're going to be trying to move that data as soon as possible, and that will be a archive of precip data that's centered around South Asia. So that might be really helpful because it's down to 4 kilometers, I believe. And another thing to explore would be the climate serve through Severe. They have CHIRPS GEF, which is from UCSB, which I think is, I don't know what the resolution of it is, but it's got a great temporal resolution, which might be to explore as well. That's great. I don't want to eat up all the clock if there's other people who have questions. Okay, I've got one more. I've actually got like 10 more, but when you were looking at these individual slope units and you're sort of exploring the interactions of these different networks associated with these slope units, did you also look at maybe characteristics of, say, a high slope, medium slope, and low slope to help categorize where the model was capturing maybe those extreme tails in if they're associated with high slope or low slope? Was that associated with that, or was it maybe a common error that you were sort of seeing, or something to synthesize about?
Actually, we looked at how the temporal, we didn't look at the extreme values on that, but we looked at how the temporal, like the legacy effect is there, like if you have a heavy rainfall this year and how every year it changes after the 2015 earthquake, like how it changed. And we found out that usually in case of medium slope, the slope was not failed during the earthquake and it failed after the rainfall. But in very high slopes that already failed during the earthquake. So the probability of having landslides was going down for high slope, but for medium slope, it was going up. And for the low slope, it remained kind of constant. Because this is mostly because like in the medium slope, even though there are fractures, it didn't really fail. And when you have a monsoon and then there is more rainfall, then it starts to fail because the water goes in and it causes the landslides. That part we looked at, but for the extreme values, we didn't have looked at how it responds with the slopes.
Yeah, I was wondering, as you're sort of showing those results, even though you're on a great one-to-one line, I was kind of thinking in my head, well, I wonder if it's really connected to the extreme slope values that obviously might be contributing to these really, really extreme events as well. But yeah, that's, I mean, it's so cool. And I'm glad you brought up that legacy effect of the lag of the water table or just hypersaturated soils, and how you're approaching that with this temporal lens. And that's something that we've been kind of talking about as to a different topic, but it's still in the soils. But we were looking at land cover and how land cover change over years may directly contribute to that as well. And I don't know if you've done any exploration into like land cover as a factor that.
No, I think not, because I just use NDVI as the dataset to represent how the land cover is, but we did not include land cover because the major problem with that is because land cover is mostly classified as different classes, and it just increases the features in the neural network. And when we have more features, it's more difficult to. We need more data first of all, and it's more difficult to train the model, because if we have, let's say, 10 classes of land use land cover, then we cannot give it 1, 2, 3, 4 because it's not an increasing value. We have to make it 10 different classes, and then it just increases the features by 10, and it's usually 2 to power n increasing, so it was a problem. So we just use NDVI and clay content and stuff like that. But I think also the land use land cover has they didn't include anthropogenic, I don't know how to pronounce it, anthropogenic landslides. So the landslide caused by road were not included in the inventory, so we didn't include the road. But usually also they are a big factor in Nepal to cause the landslides, because usually they just built a road without engineering, proper engineering analysis, and then it causes a lot of landslides. But those landslides are not included. These are only the natural ones. So we didn't have to include a road network or those things here.
Yeah, that's great. Thanks so much. Any other major questions on the line?
Yeah, I have.
I was just going to add it. Oh, go ahead, Biplav.
No, go ahead.
Okay, I was just, when Tim was talking about land cover, I was just thinking, Karis actually sent me an email last night about that new Earth Engine Dynamic World land cover data set, and I think that they have land cover as probabilities instead of classes. So I was actually going to look at that for another project today and see if I could use the probabilities instead of the actual classification bands as like an input feature for something else I'm working on.
I think that could be a better way, actually, if we could have just the probabilities instead of looking at the categorical values. Yeah. Which data set did you mention? It's neuro.
I'll find the link. It's called Dynamic World. It's like a new Earth Engine product.
Okay.
Yeah, it's like, is it like 10-meter resolution or something?
Yeah, I think it's 10 meters, and it's like a constantly updating thing that they're like serving on an endpoint.
So. Oh, okay. Yeah, global scale. Yeah, I saw it. I found it. It looks very cool.
Got it.
Yeah.
Biplav, do you have any follow-on?
Yeah. Last question I wanted to ask was, so you talked about the exploding gradient descent problem that you encountered. So I was doing a similar project using GRUs for bias correcting some of the global stream flow services here for Cambodia. And I was running into similar issue, and that was mostly because the stream flow values were going from very low to a magnitude of order higher. So yeah, I just wanted to see what your technique was to overcome that problem.
Yes. So what I did was, first of all, I added this normalization and denormalization layers. So it could learn and normalize the data set to a fixed range, let's say 0 to 1, and that was the first way I did. And the second was I lowered the learning rate. It was slow, like I had to train for 1,000 epochs, but because the learning rate was very slow, it did not explode. Those were two. And third one, you could also clip the gradients. So the multiplication factor, I could, for the second order norms, we could clip the gradients. It's called gradient clipping method. For me, like adding the normalization layer as well as lowering the learning rate worked, but I didn't have to do the gradient clipping. So those were two approaches that could solve for me.
Awesome, thank you.
Yeah, those are great tips. So I don't know if there's any other final questions, but I just want to say thank you again. This is a fantastic presentation, and if the slides aren't in the folder, please add them, because again, I want to show them to a lot of folks. This is a great example of science communication, and let's stay in contact as I publish. Try and get that the precip data published, because I think it might be really helpful. I know that was one of the limitations, and we also are trying to get Nishan, who's part of Dahlia's team, to present in this group in the coming weeks as well. So another focus on landslides. Obviously, they're not using a neural network approach. They're using XGBoost, as sort of their core for their model, but it'd be really interesting to sort of see their precip thresholding and just spark up a conversation there too. So please don't leave the group, because I think there's a good opportunity for us to get into a nice hum on landslides. Well, thanks so much. And I'm just going to give everyone back a few minutes. It has been a really fantastic presentation. Thanks.